Our next presenter comes from Bowling Green, home of the Corvette, for some of you folks who are interested in automobiles. Ed Kintzel is director of the NOVA Center and a physics professor at Western Kentucky University. I have read that the Corvette plant actively uses the NOVA Center at Western. And it has occurred to me, I was wondering if perhaps the NOVA facilities are being used in the development of the totally new Corvette, which will debut in 2013. If so, perhaps we can encourage Ed to share a little insight into what to expect. The Nondestructive Analysis Center has been a recipient of Kentucky EPSCoR funding. The center offers very unique capabilities. Western Kentucky University is the only university in North America having the technology capabilities offered by this center. Ed's presentation will briefly describe those services available at NOVA. Ed?
Okay, well, thank you. As far as the new Corvette goes, I'm more than willing to take one and drive it as a test vehicle for free. So let's throw that one out there. Thank you for inviting me to give this talk about what is for sure a completely unique facility in North America. The large chamber scanning electron microscope was acquired in 2009, and we completed the construction of the infrastructure and facility around it within the last year and a half. And some of the images on the opening page show the various stages of construction. From the upper left, where we see the microscope sitting on its acoustic pad. The center itself is located in the Center for Research and Development at Western Kentucky University. And we see an intermediate construction, and then the lower image shows the pretty much completed center as it is today. And kind of the goal now is to come to events like this, to make our presentations, to collaborate and with people from around the state. So the LC-SEM really has all the regular features of a conventional SEM. And a lot of times at these kind of conferences, we think small. But what I'd like you to do is think big, right? Small is good. Let's think big. How big? Real big, right? We can scan samples that are about 1.5 meters in diameter and up to 650 pounds. So incorporating an engine block like we see on the right is no problem, okay? We have a resolution of about 10 nanometers. And again, since we are the only university in North America, we feel we have a really good niche. Our niche is not necessarily the really small sample, right? You can go to any facility and probably scan a really small sample. But what if I have 100 of them, and I want to use this tool as a QA tool, right? And I want to scan these as part of some sort of process. Well, maybe this tool is the right one then. Some of the capabilities that we have within the instrument, we have a suite of materials characterization tools for topographical imaging. We can do elemental contrast. We have EDS for chemical analysis. We have an FTIR. If we want to look at the crystal structure of materials, we have an EBSD. We have a FIB, which will be incorporated into the instrument. It's being worked on right now, but we'll have a FIB by the end of the summer so that we can do subsurface examinations as well. One of the great features also of the instrument is that we can look at non-conductive surfaces. It would be pretty tough to coat that engine block in gold. We have variable pressure so that we can look at non-conductive surfaces as well. So what I thought I would do is talk a little bit about the instrument and then show by way of example so that you can kind of think about potential ways that we could collaborate on some different projects. So this little video clip kind of shows the inside chamber. I would say roughly it's a 5-foot cube inside. Right, so most people would have no problem getting inside of it. I often have my lunch inside, and it makes cleanup a little messy, but that's okay. The rats don't seem to mind. And what this shows is how the microscope moves inside the chamber. With a conventional SEM, maybe you manipulate the sample underneath the SEM head. What I would think this does is more what I would call a normal view. If you or I were to look at a car or an engine block, were it not for extensive resources, maybe I would sit down in a chair and manipulate that engine block in front of my eyes. But what we do it here is kind of how we would examine it. You would walk around that engine block or around that vehicle to take a look at it. And that's how we use the SEM head. We walk around that surface, and we can put it in any configuration that we want. So some of the, what I thought I would show will be some of the different ways and the different disciplines that we can cross with this instrumentation. The first is looking at the interface between art and science. How do we look at objects that have some sort of cultural heritage significance? They don't have a price. Okay, I don't want to clip a little piece off of this and study it. Well, the LC-SEM is kind of the answer to overcome that limitation. What we can do, and for example, the instrument was used to study the terracotta warriors in China. Paint was flaking off of them. Rather than try to take a little piece off of that artifact, they're able to put the entire statue inside the microscope and to examine it that way. So we have a non-destructive way of looking at artifacts. So what we've done is to start a collaboration with the Winterthur Museum in Delaware. And to the upper left, I have a view of the inside of the microscope. And you see various silver objects towards the front of the microscope, just kind of for staging purposes. This isn't how we exactly scan them. Anything from the left, you see a rectangular silver cigarette case. We see a large silver plate, a smaller salt shaker, and a sander. And the great thing about this is, in addition to the other objects that we have in the back, we can put all these into our microscope all at one time and scan them one by one. The other unique thing about the instrument is we can bring all these tools, all these examination tools at one spot. Right? Normally you'd have to go maybe to 1 or 2 different machines to carry out all the measurements that you'd want to carry out. But we can bring these all within the same chamber. And we can do them all at the same time, in addition to have other objects in there so we can carry out multiple studies at one time if we really wanted to. And I've shown some images that we carried out from left to right. The left image showing examples of some pitting morphologies and surface inhomogeneities from the cigarette case on the left. The center left would be of the plate. We have the small shaker hole, which is on the second to the right, and then finally a pattern on the large sander. And we have the EDS below, which shows the presence of maybe cleaning solution or phosphates, and also copper sulfide. So we can carry out all these measurements all in the same chamber. Moving from the world of art to the automotive world, someone is driving my vet, I see. But we can do an interrupted monitoring process. So one of our other niches is that we can take parts in and out of service. So for example, if I had a Corvette rotor, the high-end Corvette rotor is about $5,000 a rotor. So how many of those rotors do we want to destroy to examine them and to look at them? I would say probably not too many, but what we can do is we can take a pristine rotor, take it, scan certain spots, we can put it into service, drive it for a number of miles, and then we can put it and scan those exact same spots again. Right? So we can do a kind of an interrupted monitoring to get kind of the living history of that rotor. Our coatings behaving as they should. One of the things that we wanted to take a look at was the Corvette rotor on the right, and you can see the stress fractures after use, they're radial, and is to compare that rotor where they cast it and then drill the holes to one with Porsche, which casts them with the holes in them. putting them under the same kind of load and the same sort of use, how do they both behave? And to compare that manufacturing process. And then I provided a couple images of that rotor on the bottom. So really, including tires, right? We could put the whole tire inside. So if you had a NASCAR tire that is blown out, we could put the whole tire in there, and to see how those reinforcing structures had behaved. Was there something within that tire that failed? Why did that tire fail? And so really anything that can wear, that can fail, we can study by way of this interrupted monitoring process. Yes. One of my favorite collaborations is with the Four Roses. Highlights the variable pressure capability of the instrument. Four Roses, not too far away. I had a nice visit there yesterday. And what it highlights is if we took the barrel stave, we would have to normally clip off a piece of the barrel stave, and we could study that in a variable pressure SEM. I can take the entire barrel stave and put it inside the SEM and take a look at any part that I want to. So what we did was we looked at the barrel stave inside and analyzed that there were calcium deposits inside the unused charred white oak barrel. We can also look at diffusion of the product, maybe over time, what's diffusing, analyze different things that we find inside of the wood. And then we can also look at how the wood's actually wearing or behaving over a period of time. And then really the other one was just we looked at the metal band that was around the barrel. But really I think this highlights the fact that we have the variable pressure capability within the instrument. Also, one of the probably most used materials on Earth is concrete. How do we make a stronger, lightweight, more lightweight concrete? And one of them could be the introduction of fibers. These happen to be a polymer fiber. We will start some measurements coming this Monday where we've integrated nanotubes into our concrete to see when that concrete fails, we put it under a stress. Do those fibers bridge those fractures? Do they bridge those gaps? And I've shown a couple images of the concrete fibers, again highlighting the variable pressure capability that we have, and then showing on the bottom two images how our concrete, where it looks disorganized on the surface, if we look at where it popped open, we can look inside that hole and see that, well, maybe it's not quite so disorganized as these platelets have formed underneath those bubbles. Some forensic science. I actually have an intern working for 6 weeks from EKU, working on some fire science projects. So some of the things that we do want to explore are integrating some educational programs into that facility as well. So one of the things that we looked at, tool markings. It's not a human bone. It's about 1,000 years old. It's found in a cave in Kentucky. And we see the tool marks that run from the upper left to the lower right. So one of the things is how do we identify what tool was used to, for lack of a better word, remove the flesh from the bone. But we can use this for forensic studies as well, again, using the variable pressure capability of the instrument. We can also take a look at, using the EDS, we can take a look at different parts of the bone and to see what's present so we can learn something about the environment with which that bone was found for all that period of time. One of the other things that I started thinking about was if we had a handgun and we wanted to, and the serial numbers were tried to be eradicated off of the handgun. I was able to acquire from a local police department. And what I did was first to look at the surface to see what do we have left. And we can see, well, if you look at the upper right and the lower left, you can still see some of the letters. We could do EDS, and we could do an EDS mapping of the surface to see where those elements are present. Maybe it brings out some more detail, maybe not. But the last part, the part that I would like to try, but I probably need permission to further destroy the serial numbers on the gun, lest I find myself somewhere else, would be to polish that surface down smooth, because one thing that they can't change, what they can't scratch off, is once that material is stamped, they change the crystal structure underneath where it was stamped. And what I can use then is a diffractometer, which is inside the instrument, and look for changes in the crystal structure. So not that this is the only technique to extract serial numbers off, but as an alternative. And the nice thing about this is that we did not have to cut that little piece out of the gun. We could put the entire gun inside of the instrument and then give it back once that study would be carried out. We also had some fossils. Again, a different discipline, right, as we move across from engineering and forensics. Again, non-destructive. We had some smaller trilobite samples that we had put into the instrument and looked at different parts on the surface to determine what different minerals were present. In astronomy, we had some impactites, a piece of a moon rock. No, not one of the real moon rocks, didn't go to the moon, but one that was found in the desert. So we looked at that as well. And the lower left, we had a Fresnel lens. This was part of a collaboration that we had with a University of Alabama, Huntsville. This was a NASA EPSCoR funded project. And that will be continued on. I go there next week. We're talking about continuing on our collaboration, where they had some Fresnel lenses. And we started scanning these to look at the facets that were on the surface, as well as potentially the surface roughness. So now we want to expand that collaboration with them to not only look at the Fresnel lenses, but now to look at some of the optics that they're creating for different mirrors and things. We had fuel cells. We had a fuel cell we can put inside the instrument. Yeah, we can image a fuel cell, but what they were interested here was the oxidation on the solder. And we can look at different spots and see how they're behaving as a function of time. I talked about forensics a little bit more, forensic engineering, where we can really study materials, products, and structures, components that have failed. A lot of times those failures turn into a personal injury problem, right? This instrument could be used then to take that evidence, and I just found this example online somewhere of a broken fuel pipe. We can take this entire fuel pipe, put it inside the instrument to try to interrogate it to learn exactly why did it fail. Was it a mechanical failure? Was it a chemical failure? We had one project where we were going to look at O-rings to see if it was a chemical degradation that caused a failure in an O-ring, or was it some sort of mechanical process. So this would be another area that we would like to get into for some future collaborations. There was a small drilling tool, so small manufacturing processes can be carried out inside the instrument. And I'll show some examples of some dynamical processes as well. So let me show some of these. We had a three-point bend test where we can watch the crack development using the instrument, and we can watch that fail real time. I think it's about 30 frames a second. So the dynamic testing is also something that we can't necessarily carry out with a conventional SEM. We have a collaboration with UT Knoxville where we have a small load frame that's going to be integrated. This is going to also be in collaboration with Oak Ridge Lab. We're looking to develop a similar load frame that will go into the Vulcan instrument, which is an engineering diffractometer. We see the surface so well. They don't see the surface so well. So we can combine the two techniques to give their user community some additional information. And I'll show some of the things that we can do. We can analyze the stress, but at the same time, we can look at how the crystal structure changes in addition to watching that material fail. Let me just show some of the other little quick video clips. We can watch the holes develop, and we can see elongation of the grain structure in the material, crystal fracture, and then we had a carbon composite that we can make fail, but we can watch the failure. And I think really that's the unique part of the instrument. And so hopefully that gives you a good flavor for all the things that we can do. I've tried to think of a lot of things. There's probably things that I'm not thinking of, but at least it can get us talking as a group about things that we can do. So with that, we're looking to develop new collaborations, and thanks for your attention.